Hello and welcome back, and we're still on the properties and structures of matter, and today we're looking at the Bohr model. Now the Bohr model, I know it sounds like I'm repeating myself all the time, is something that we have looked at in stage 4 and stage 5. We're going to look at it a little bit more in detail and look at some of the advantages of that model and some disadvantages or some limitations of that model. So the Bohr model, it was proposed that the electrons revolve around the nucleus and they are in fixed circular orbits. And each one of those orbits corresponded to a specific energy level. And he also pointed out that electrons can only occupy one energy level. Now, he also found that the larger the radius, so the bigger the element was, the more energy that it had. So this worked really well for hydrogen, and that supported his evidence, which allowed it to be considered as the current model for a period of time. And what he said was an electron will emit or absorb energy when it jumps from one energy level to another. And as it comes back down to its ground state from its excited state, it will release some energy in the form of a photon of light. Now, we now know that the assumption of circular orbits was incorrect, but his insight there was that the electron could only occupy certain regions of space, which we now know with future models not to be the case, but Bohr's model is certainly very good for explaining certain aspects of the element's structure. So if we look at Bohr's model of the hydrogen atom, what he actually would find was an atom remains only excited for a brief period of time, so we heat them up, and you'll notice that in your flame test they don't take very long. So what would happen was after a short interval, only sometimes 100th millionth of a second or so, it'll drop back to its normal ground state, and in doing so will emit some light. And so therefore we call this an emission spectrum. So what might happen though is that electron may jump back in one jump, but it may also jump back in a number of different steps. So it could be 2 or more jumps, stopping at intermediate levels on the way down. So we're not saying that it just jumps from the first shell to the second. It might go to the 5th shell and then jump back to the 4th, 3rd, 2nd, and so on. And with each jump, it will emit a photon, which corresponds to a wavelength of light. So in the case here, we can see that we've got a photon of light in this region, and then we've got these other photons of light that correspond to different wavelengths in this spectrum here. So each one of those lines correspond to that jump. So we can see that there's a number of jumps, and hydrogen just has one electron. So it was a lot easier to explain. Now, when we look at this, the emission spectra that we get for hydrogen is a combination of each of those different colors there, and which one may be brighter or more distinct will obviously have a little bit more of a sway over what color it totally emits in general. But these are the emission spectras that are produced for each of the elements that enables us to determine what elements are present in stars and so forth when that light is actually put through a prism and produces its own spectrum. So the problem with the Bohr model was it did have some limitations. It was really good at predicting for hydrogen, but it wasn't able to predict for elements with more than that one electron. And he also wasn't able to predict why did we put 2 in that 4th shell before filling the whole 3rd shell. So it was a big step in the right direction, but it wasn't the full story. So if we have a look here, we can see the spectrum of hydrogen, but we can also see the spectrum of a great number of other elements here as well. So Bohr couldn't explain why the electron should only be restricted to one orbit, and despite a whole lot of work that he might have done, he couldn't explain the spectrum for any of the other elements other than hydrogen. So it had one proton, one electron. It was a lot easier, and it was easier to explain the transitions. But when there was multiple electrons jumping to multiple levels and producing their spectra, he wasn't able to do that. So with those heavier atoms, they had a great number more transitions and so on. So similar pictures can be drawn for all these other elements, but you can see here some of these other elements that we might have seen before with our flame tests as well, and they're a lot more complex. So with neon, you can see a lot of the transitions and the steps that were coming back, and the photons of light corresponding mainly to that reddy yellow area of the spectrum. So its light that it produces is that reddy colored light that we see. Sodium again produces that orangey kind of color as its spectrum as well. So each atom has its own unique set of spectral lines, and then scientists can actually use that to determine what elements may be present in certain samples and so forth. So you would have done a flame test. We did that before just to spark your interest. A flame test is the technique using that knowledge that we've just looked at, that different metals emit different frequencies of light, and each of them have their own signature color. But that color is a combination of all of those different lights or different lines that we have seen on the spectrum. So what is the cause of this? I know some people have asked that already. Electrons orbit in distinct energy levels. If we provide some energy to those, they jump up, they jump back down to their general state eventually, and giving out energy in the form of light and different colored lights as it goes. We can pass those through what we call a spectrophotometer, through a prism, and it will produce a spectrum for each one of those elements. So with our emission spectra, it helps us actually tell the electronic structure of the atoms. So atoms of the same elements will produce the same spectra. Each one has a different one, and therefore it's telling us a lot about the color. So why does each different element have its own color? As it's heated, it's got different electrons that will do different things, producing the different spectral lines as it drops back down. The collective color that we see is a collection of the lines that we see giving one unique color. So you can understand then why some might have similar colors, even though they may have different spectral lines. Anyway, we'll talk about it a bit more in class. See you then.